Hi, welcome back to Mathematical Logic. In this video, we're going to talk about the Tableau tree or the refutation tree method for first order logic. So we've talked about this method when we discuss propositional logic. So all the rules from propositional logic can still be applied. And then we have 4 new rules for quantifiers. Here's the first rule called the universal quantification rule. This says that if you have a well-formed formula of the form for all x, b, where b could be any expression in predicate logic that appears in an open path. So you have this expression that appears on an open path of the tree, and if you have b is a name is a name letter that occurs in some well-formed on that path, then replace all occurrences of x by b, and then write the new well-formed formula at the bottom of the path. So that might be confusing. So when we do example, this is actually really simple. And so a couple more things I say before I'll show you an example is that if and only if no well-formed formula containing the name letter appears on the path, then choose any name letter a as above. So if you have no name letter, then you can pick any letter you want. For example, a. And in either case, we don't check off this well-formed formula. Remember that from propositional logic, whenever we essentially replace a well-formed formula with another one, we're using the tree branching, we cross off or check off the previous well-formed formula. In this rule, we actually will not check it off, and the reason is because this well-formed formula is true for all x. So when we replace it with, when we add another well-formed formula that for the sentence with a particular object, we don't that adding that extra sentence is not equivalent to having this general statement. So we can never check off this statement. So we'll see this as we do some examples. And so this rule is basically, it's a formal expression of the fact that whenever something is true for everything, if this sentence is true for everything, then certainly it's true for one particular individual of the domain. So here's an example. So all frogs are green, everything is a frog, therefore Alf is green. So let's write this in predicate logic. For all x, f of x implies g of x. For all x, f of x, therefore g of a. So if everything is a frog, and all frogs are green, then everything is green, including Alf. That's basically is the reasoning. So let's prove this by using the tree method. So here's the 2 premises. And well, as before, when we try to prove entailment or logical implication, we negate the conclusion. So here's the conclusion negated. And we want to basically, if this tree can be closed, then that means that we do have entailment. And if the tree is open, then we don't. Okay, so here's the universal quantification rule. It says that since a is a name letter, just an object in our domain, we can, because this, for example, this first statement is true for all x, certainly it's true for a, so we can take this statement and write a in place of x. So we're replacing x with a. So now f of a implies g of a. Because this is true for all x, it certainly is true for a. So that's basically all the quantification rule says, is that any letter that we see, any letter that represents some object, can be replaced for x in the for all x quantification sentence. And then also this is true too, but this is for all x f of x, therefore certainly f of a. And notice we don't check these off, right? We don't cross it off because this statement is not equivalent to this statement. This is one person for which this is true, so we don't cross this off. And now this sentence right here, f of a implies g of a, this is propositional logic. So I can apply the rule that I saw that we learned previously, namely that you have a conditional, then it branches off into not f of a or g of a. Now this we can cross off because when I put this branch is equivalent to this statement, so I can cross it off. And notice now that we have that this is closed because not f of a, so that's a contradiction, so we close it. G of A, not G of A, that's a contradiction in that branch, so we also close that. So this tree is closed, and therefore this is valid. Okay, here's another example. These are the premises. For all x, f of x implies g of x. For all x, g of x, not f of a. This is kind of similar to the previous example. We're trying to prove f of a, so we're going to negate f of a. Okay, so again, here's a is an object, so we're going to replace a right here. So f of a implies g of a, just like before. Same thing for g of x. We put g of a there, and then we're going to branch as before, not f of a or g of a. But notice in this case, we can't close this tree. This branch is not, there's no contradiction, and this branch also no contradiction. So that means that this is not a valid logical implication. Yeah, by the way, we can also cross this off, but okay, so this is invalid. So this says that even if it's true that for all x, g of x, and even if it's true that that for all x, g of x, it does not imply that there exists an a, f of a. So, and also just like before, an open branch tells you a way to find a counterexample essentially to this. In other words, there exists an object A such that is G but not F, and that satisfies the premises but does not satisfy the conclusion. Therefore, A is our counterexample to this argument. Therefore, this argument is not valid. So here's the next two rules. These are negated, universal, and existential rules. Essentially, an equivalent form of De Morgan's law. We have this negation, so we want to bring in the negation or distribute that negation essentially. So this is really simple. If you have, if it's not true for all x beta, then we can bring it in and say there exists an x such that is not beta. Right? And so if it's not true that everything has a certain condition, then that means there exists one thing that doesn't have that condition. And in this case, we do check off that well-formed formula, as we see later. And here's the negated version of the other rule, which is the existential quantification. If it's not true that there exists an x beta, then that means that for all x, not beta. So again, we can think about that and make sure you understand that these are equivalent. So let's see how we can use these two new rules. And basically what this rule says is that if you have a negation outside, you always want to bring it in. Because once we bring it in, then we have some form of the universal or existential rule, which we can then apply. And so always our negation outside should be distributed inside. Okay, here it is again. Again, we write our premises and then we negate the conclusion, which is a double negation. We can certainly resolve this, but I think we're actually going to not do that. I'll show you how this is going to be done. So for example, this is applying that negated existential rule. It says that if you have a negation here, you bring it inside and becomes, instead of if it's not true that there exists x g of x, then for all x, not g of x. And this statement is equivalent to this, so we can check this off. And so that these are the same, so we check it off. And then now, for all x, not g of x means that, well, here's an object A, so I can put A inside of that and say not g of A. If it's true for all x, it's true for A. And notice, by the way, we cannot check this off because this is not equivalent to it. And the next thing is we're gonna this A right here can be put over here also because of the for all x. So f of A implies g of A, and now we're gonna branch not f of A or g of A. And notice now that we try to close this tree, and we'll cross this off because that's equivalent to the branching. And both of these branches are closed because not f of A contradict with not f of A, and then g of A contradict with not g of A. So that means this argument is valid. Okay, let's see. How about this one? This is for all x, f of x implies that for all x, g of x. And then it's not true that there exists an x, g of x. Then we want to prove that there exists an x, not f of x. Okay, so these are the premises, and then here's the negation of the conclusion. Okay, so again, we're going to use that negated, one of the negation rules. So we're gonna distribute this negation inside of the they exist, so that this is now for all x not g of x. We can cross that off, and then we'll do the same. We're gonna branch next. So this is the conditional rule. So notice that this universal quantifier only applies to this part, and this applies to that part. So these are two separate parts. I can break it up into not this or that. So this is now this branching is equivalent to this, so I can check this off. This is actually doing the rule for propositional logic. So this first statement can now be crossed off, and now I can apply the negated rule for this, which says that actually sorry, I'm going to apply the negated rule for this. So not for all x, f of x means that there exists an x not f of x, so I can cross that off. And then notice that now I can close this branch, because this is there exists x not f of x, and this is not there exists x not f of x. So this is exact opposite of this. So this is a little bit trickier, but this is as a sentence in predicate logic, and this is its negation, and so we can close that branch. And on this side, we're gonna apply g of. By the way, we noticed that we don't have any a anywhere here, right? There's no object. There's actually no constant or named object here, and so because this is true for all x, I'm going to introduce a variable a. So I'm going to say g of a. It's true for all x. Let a be any object, and I'm going to say g of a. And we know because in predicate logic, our domain is non-empty, so there's at least one object, and whatever you call it a, then certainly we have a g of a. And then notice that this right here for all x not g of x, I can apply a now to not g of a, and now this also closes. So this is valid. Okay, here's another one. There's just an x, f of x, and g of x, and then we're going to negate the conclusion here. By the way, it's good to try to understand this in the context of example maybe or interpretation. This says that if there's exists an object that is both f and g, whatever the interpretation for f and g you might have, then certainly it's true that there's an object that is f and there's an object that is g. So you can try to understand that, and then we can prove it abstractly in this case. So here's the negation of the conclusion. Again, there's an x, f of x, and g of x. So I want to replace x with a. So did I? Okay, yeah, I didn't skip anything. Sorry, I'm gonna make sure I'm not. I feel like I skipped something, but yeah, I think I might have put this ahead of time. Sorry. So yeah, let me put this slide. Sorry for the confusion. I actually put this after this. Actually, I haven't discussed this rule yet. So yeah, sorry about that. So here's the last rule, which is the existential quantification rule. It says that if you have the exists x beta that appear on an open path, check it off, and then choose a name letter b or whatever it is that does not yet appear anywhere on that path. Then replace the coordinates of x by b, add it to the bottom, and then check it off. So this rule says that if there's an existential quantifier of a well-formed formula of the form that exists x beta is true, then there has to be an object for which this is true, and we can give it a name for that object. We may not know what the object is. We can give it a name, and we can check off that well-formed formula. So here's the example for it. Yeah, so suppose that we have, since we have an existential quantification here, there's x, f of x, and g of x. Well, let's give it that. There's an object that satisfies this, so let's give that object a name. Let's call it a. Doesn't matter what you call it. Call it b if you want. F of a, g of a. So this statement is actually equivalent to this, so we can check this off, right? Because by giving a name, then we have already stated that that there's an object that satisfies this condition. So we check that off. Then f of a and g of a is from propositional logic. We just write it in the same path here. Cross that off, and then we're gonna apply De Morgan's law. Again, this is just part of the propositional logic Tableau tree rule that says that you have not something and something else. That's the same thing as not this or not that. So that's the branching. Again, this is not predicate logic rule. This is actually just propositional logic rule using De Morgan's law. And then now we're going to apply negation to this. So we can cross this off because this is part of the propositional logic rule. And now let's look at this and say, well, I can bring this in and say for all x not f of x, and cross that off. And because this is true for all x, certainly it's true for a, so not f of a. And notice now we can close off this branch. This is the f of a, not f of a, is closed. And on this side, same thing, bring in a negation for all x not g of x. Just do it for, cross it off, and then do it for a. And notice we also close that off. So this argument is valid. So we do have entailment in this case. Okay, here's another one. Okay, so again, here's the premise, here's the negation of the conclusion, and then we'll bring in the negation. So for all x not f of x and g of x, cross it off. And then this is an and, so I can just write them on the same branch. This is propositional rule, so I can cross that off. So, and then now we can apply the existential rule. It says that f of a, there exists an x f of x, so call it a. And notice next, there exists x g of x. I cannot call it a because a has already been called. We already name an object a that satisfies this sentence. So we can't use. We don't know that this x is also a. So it could be a, but it might not be. So we're gonna call this b. So the next one is there's an x g of x. We'll call it b instead. Cross those off. And then we'll apply a and b to the for all. So that not f of a and g of a, and not f of b and g of b. And then I'll branch out. This is De Morgan's law. Not f of a or not g of a. And notice this closes this branch. F of a, not f of a. So I can close it. So I don't have to worry about this branch anymore. Let's close it early. And then on this side, I'm going to do that De Morgan's law to this part. Notice I don't have to do it to this side because we're close to that branch already. So let's do it to this part. And then notice this is also closes, but this is actually open. This branch is open. We found a counterexample that makes the premise true, but it makes the conclusion false. And so this is not valid. Okay, so here's for something a little more complicated. We have a series of quantification rule, and notice, remember that the law of the order of operations that we go. You have a bunch of them. We go right to left. So there's an x such that for all y, L of xy implies that for all x, there's a y, L of yx. So we want to prove this. So again, we have the premise and then the negation of the conclusion. Okay, so let's first apply the existential rule. There's an x such that this is true. So let's call this x a, and then put a in place of x, and then leave this alone. So this is so that we can now cross this off. And then let's distribute the negation. So now there exists an x, not this. I can cross that off. And now let's apply the existential rule again for x. But this time, we're going to apply it, because again, we already used a, so now this existential, we're going to call it b. So there does not exist a y, L of yb. So replace x with b. And then cross that off. And then bring in the negation, distribute the negation inside. So for all y, not L of yb, cross it off. And now we're gonna apply the universal rule to this by this is true for all y, so it's certainly true for a particular y, for example b. So let's do if I put a b here, you have LAB. If I put a b here, I have not L of yb. So there it is. There's our contradiction, and we can close that tree. So this is valid. Okay, finally, so that's basically the 4 rules that we need for predicate logic. But so here's an identity relation. This is a predicate. It's a binary predicate that's very useful in math. It's the identity relation. So this is, again, think of this as in predicate logic. This is a binary predicate. It's a predicate that has 2 argument, and it just means x is equal to y. So the identity of xy means that x is equal to y. So for this given interpretation, each object in the domain is equal to itself, but nothing else. So we can extend the Tableau tree method to include this extra predicate because it's so useful in math. So this rule is very simple. It says that if you have A equal to B on an open path, and you have another well-formed formula, say beta, and that has either A or B in it, then we can replace any occurrence of A with B or vice versa. We basically this is basically a substitution, right? And we don't check off any of this. And then there's also the negated identity rule that says that if you have an open path that has this well-formed formula, not A is equal to A, then that's a contradiction because A is equal to A. And so if you have a not, then we can close that path. So we have two new rules here for this predicate relation identity. Okay, let's prove this. So here's the entailment that says that given no assumption, this is always true, right? So we don't need any assumption here. So sometimes this is called a theorem. So for x, for all y, if x is equal to y, then certainly y is equal to x. And that makes sense. And so we want to prove this is always true for all x, for all y in any interpretation. And so to prove it, we negate the conclusion. Okay, so again, we apply that negation rule, bring it in. There's an x, such that this is not true. Cross it off. And then, because there's this an x, so we're going to replace x with a name variable, say a. So not for all y, a is y, and y is a. So replace x with a. Cross it off. And then again, I apply the negation again, bring it inside again. There's a y, so it's not true that a of y implies y is a. And then, because there's just a y, we're going to replace y with another variable, called say b. And so now it's not true that a is b implies that b is a. And then now I can apply the propositional logic rule for the tree method, which says that if you have a conditional and you have negation, you can so a conditional is essentially as an or, right? It's actually not this or this. And so when you apply De Morgan's law to that, it's this and not that. So yeah, crossing off the previous one. And then so these two right here is basically equivalent to this. Again, this is a propositional logic rule for conditional. So this is an and, this is an or. So when you do De Morgan's law to it, you have an and. And so A and B and not B and A. B equal to A. A is equal to B and it's not true that B is equal to A. And now because we can now apply the identity rule that says that if A is equal to B, then we can replace any occurrence of A with B and vice versa. So let's replace B with A, for example. And we have that, and now it's not true that A is equal to A. And so again, this is applying the first of all applying the identity rule that says that we can substitute B for A, and then finally this is the negated identity rule. It says that if you have this negation, this is a contradiction, so you can close up that path, and therefore this is valid. Okay, so this is basically the tree method for predicate logic. A little bit confusing, but we have to get used to this, and hopefully the homework will help. Okay, thanks for watching.